Welcome to the next video on measure theory and probability. This is video 12 on the equality on generators. Be a little more clear on what that means in a second. So this corresponds to part 1, chapter 1, section 4 of the textbook. And so what we're going to prove in this video is the following theorem, which effectively gives us a very useful sort of condition to decide whether or not some two measures are actually the same measure. And that's going to be important later on. I'll talk more about this later, but one thing that's going to happen eventually, as I kind of keep repeating, we want to get a measure on the sets of real numbers which is consistent with interval length. And when we build it, it may have a little bit of a sort of feeling like it seems perhaps a little strange, right? Like when we actually build the thing, maybe it's not crazy, but at least I think it leaves me and possibly some other people with the question, well, this is not built in the way that I would have predicted. And so then you are left wondering, well, could we have built some other measure which was consistent with interval length? And what this theorem is going to guarantee us is no, actually, if you built a measure in any other way, it actually must be the same measure as the one we built. So there's no point in looking for any other way of building such a measure because it'll always come out to the same thing as what we will construct, right? So the uniqueness of measure will just kind of guarantee that when we do eventually build this, like generalization of length measure, in some sense, it's the only one you could build, so it must be the right one. So let's go ahead and state the theorem. Suppose that you have some two measures, mu and nu, on a shared measurable space, EA, and let's suppose that we have some generator, this collection C. And moreover, let's assume that mu and nu both agree on the generators, right? So this set A is anything in the generator. We're going to break this theorem into two parts. The first part is going to say that if the measure of the entire space is finite, which is to say if they have finite equal masses, then the two measures must be equal. And then once we're done with that, we'll move on to what is perhaps the more useful version of this, but right, we'll use 1 to prove 2. But 2 is perhaps the more useful one because that's the one that will actually apply in the case of measuring sets of real numbers consistent with interval length. This one says, suppose that you have some sequence in your generators such that their union is the entire space, and suppose that the measures agree on each term in this sequence and that each one is finite. So rather than just kind of outright assuming that the measure of the entire space is finite, like this one allows for the measure of the entire space to be infinite, we just need to have some kind of sequence where it builds up to the entire space and along the way, each part of it is finite or has finite measure anyway. So in that case also, the two measures are equal. Okay, so for the proof, right, we are, I think increasingly we should feel more and more comfortable with the idea that the way that we're going to approach these proofs is by defining some kind of a subset of, in this case, A, but show that it is a sigma field containing the generators, and then that will imply that it must contain the entire A, right? We've been using this strategy for a little while now, and in this particular case, I think it makes sense that we would define this set G, and we would want to show that this set G is, a collection containing C and a sigma field, right? Because after all, it's just the set of all things on which the two measures agree. And by the way, maybe I should emphasize this. We are assuming that the two measures agree on the generators and trying to prove that the two measures are equal. When I say that the two measures are equal, what that means is that they give the same value for every possible input. So, here, right, we're effectively saying the set of all things for which they give the same measure, if we could prove that that just is the entire space, it would imply that mu is nu. So, okay. So that's our strategy, right? We're going to try to show that G is a sigma field containing C. And in fact, to show that it is, right, like showing that it contains C, that's nothing at all. That's one of the assumptions of the theorem. So we don't even have to do that part. But we do need to show that it is a sigma field. Well, because of the previous video, or at least an earlier video, we have a new technique for showing that, which is to show that instead it is a monotone class, because after all, we are assuming that the generators are closed under intersection. So, okay, so that's going to be our strategy for this proof. We're going to show that G is actually a monotone class, and it'll follow that it's a sigma field. Okay, now to show that it is a monotone class, we have to show that the entire space is in G. Well, that is really trivial for the first part because we already have that, that the two measures agree on E, and so E is in G. Okay, let's take a quick look at showing closure under monotone relative complements. That is just my made-up name on the spot for that second property that defines what a monotone class is. Anyway, when we get into it, hopefully it'll ring a bell. So what this property requires is that we take any two things from our collection, right, any A and A prime from our collection, such that A is a subset of A prime. We want to show that A prime minus A is therefore in the collection, right? That's the property of a monotone class that we're talking about right now. So because we know that A and A prime are both in G, then that means that, and I wrote this completely wrongly. Don't know how I made that mistake, but so we must have that mu and nu both agree on A and also on A prime. Okay, so that's what we get from knowing that A and A prime are both in G. Now, we are assuming in this part that the measure of the entire space is finite. Well, each of these necessarily are subsets of E, right? So since A prime is a subset of E, then by monotonicity, we get that the measure of A prime is less than or equal to the measure of E. Also, the measure of A less than or equal to the measure of A prime. Anyway, all of this demonstrates that the measures of everything involved are finite, and because they are finite, we can apply excision. Well, excision, especially, it applied in kind of the most obvious way here, would be to take, let's say, mu applied to the set difference, A prime minus A. We use excision to get mu A prime minus mu A. Term by term, we can replace them because of these equalities that we established a second ago. And then we can, again, apply excision to put them back together in nu. And ultimately, we're showing that mu and nu both agree on this set difference. The upshot of agreeing on the set difference, I probably should have written it, but I'll write it now, is that A prime minus A is in our collection G, and this shows us that G has that closure under monotone. And I guess I should also point out, or I guess I don't need to point out that they're subsets because we already said that. So anyway, so we have that closure under monotone relative complements, and so we've demonstrated that property. Now, I won't go through the property for monotone unions, countable unions. It should be relatively easy, but as always, if it's not, then leave a comment and I can try to fill in the gaps there. But for now, at least, I am going to skip that part unless anybody requests that I fill it in. Okay, so we are now going to move on to the second part of this theorem, and we cannot assume that the mass of these measures is finite, that is to say the measure of the entire space is finite, but we do know that there is this like process of building up to the entire space through this monotone increasing chain, so that kind of along the way at each finite step, it has finite measure. And so a natural way to approach this is to say, well, maybe I can just sort of apply the previous result to each stage and see where I go from there. So to do that, we are going to define the restriction of mu and nu for each n, right? So fix any particular n, natural number, and we'll talk about this E sub n that kind of builds up to the entire space. And for that n, we will define these new measures, mu n and nu n, to be the restrictions of mu and nu to en. Now, what does that mean? I kind of skipped this, and maybe I should make a video on this, but the restriction is defined in a fairly, straightforward way. So maybe I just won't talk about it here. If anybody has any questions, I'll just make another video and sort of insert it back in the playlist. But in any case, right, we take mu and nu to be the restrictions, mu n and nu n to be the restrictions of mu and nu, defined in a reasonable way. And so that the previous part applies to mu n and nu n. Okay, so we have that mu n and nu n are equal to each other because of the previous part. Now let's talk about just taking any measurable set and arguing that mu a must equal nu a for this measurable set. Now, since this forms a sort of monotone increasing chain, then I think that's kind of a big hint that we would use continuity from below, because it's building up and up. And so we would like to try to express this in some way as this monotone increasing chain of sets that we take the union over. Well, it should be very obvious and straightforward that A is equal to the union over all A intersect En. I'll let you prove that for yourself if you like, but I take that as not hard to understand and not hard to prove. So with that in hand, we can apply continuity of measure from below. We get this limit of the measure mu on A intersect En. I guess I should remark that this is then in fact the same thing as lim n to infinity, the limit of the monotonically increasing sequence mu n of A, right? So if you go back and check what the definition of the restricted, right, mu restricted to a set, blah, 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 you'll see that these are equal. And then this is the same thing from the equation that we developed above. This is the same as lim n to infinity increasing nu n. And then, again, by definition of the restriction, you get the lim of nu on A intersect En, and then do another, right, like, I'm skipping this step for nu, but of course, right, like the next thing to do would be to talk about the nu of the union, and then that is the same thing as nu of A. So just kind of running things backwards the same way that I ran these parts forwards gets you to this final result, that you get nu A. This shows that mu and nu agree on every single member of every single measurable set, and therefore mu must equal nu, so the proof is complete.